Welcome to The Explainer. You know that feeling when you're looking at a C programming problem and it feels like it was specifically designed to trick you? Well, you're in the right place. Today, we're going to break down how to get inside an examiner's head and solve those problems with confidence. Yeah, that's the big question, right? And the answer isn't about memorizing more syntax. It's about understanding the strategy behind the question itself. See, the toughest problems are designed to test your real grasp of how the language works under the hood, not just if you can write a simple program.
Okay, let's dive right in. If you want to outsmart the examiner, you've got to know where they're going to focus their energy. We need to look at the blueprint, see what topics really matter.
So take a look at this. This table breaks down exam questions over the years, and a really clear pattern just jumps out. Yeah, of course, the basics like control flow and data types are important, but look at the heavy hitters at the top. Pointers, strings, functions, and recursion. These are the big ones every single time. And why? Because these topics are where examiners can really test if you get the deeper concepts of how C handles memory and logic. It's what separates someone who just writes code from someone who truly understands it. So let's jump into our first examiner trap. I call this one the devil in the details, because man, it looks so simple on the surface, but it's built to test just how precise you are with operators. At first glance, you look at this code and it seems pretty simple, right? Just a few character variables, some math, no problem. But that's the trap. The combination of bitwise operators, the ampersand, the pipe, the caret, mixed with regular character math is a classic tripwire. It's designed to catch you if you're not paying close attention. Okay, so here's the absolute key to this whole thing. The computer doesn't see P or X. It sees their ASCII values, in this case 80 and 120. And those operators, they're not logical, they're bitwise. That means they work directly on the ones and zeros that make up those numbers. This is a sneaky test to see if you remember that, deep down, a character is really just a number. All right, let's walk through the first part, A and B. What we do is line up the binary code for 80 and 120. Now, the bitwise AND is simple. A bit in the result is 1 only if it's 1 in both of the numbers about it. You do that all the way across, and you get a new binary number, which, what do you know, translates right back to the decimal number 80. And now we can put all the pieces together. For that first variable, C, we take our result of 80 and add the ASCII value for the star character, which is 42. That gives us 122, the ASCII code for a lowercase z. For D, the bitwise OR gives us 120. We subtract the ASCII for the dash, 45, and get 75, which is a capital K. And finally for E, the bitwise XOR gives us 40. Add the ASCII for the plus sign, 43, and we get 83, which is a capital S. And there it is. The final output is ZKS. It's a result you'd never ever get unless you meticulously tracked every single step and remembered the difference between a character and its numeric value. A perfect little examiner's trap. All right, on to the next one. Let's explore another favorite challenge, recursion. Examiners just love recursion because it forces you to build a mental map of how a program actually flows, especially when it's calling itself over and over. This function right here, it's beautiful. So elegant. It reads a line of text you type in and prints it out in reverse. But hold on, look closely. There's no array, no buffer, nothing to store the string. So how in the world does it remember all the characters to print them backward? Well, the secret is something fundamental to how programs run. It's called the call stack. The best way to think of it is literally like a stack of plates. Every time a function gets called, a new plate is put on top with all its info. When that function is done, its plate is taken right off the top. So let's trace this with a real example. Imagine you type cats and hit enter. The first reverse call reads the C and then immediately calls itself. That new call puts a plate on the stack, reads the A and calls itself again. Another plate. This one reads the T and calls itself again. Finally, the last call reads the new line, the enter key. That's the base case. So now the stack starts to unwind. The very last function is the first one to finish. And what does it do? It prints its character, T. Then its plate comes off. The one below it finishes, printing A. Then its plate comes off, and so on. It's like this perfect chain reaction, all in reverse. All right, time to venture into what, for many, is the scariest part of C, pointers.
We are about to navigate the memory maze of some seriously complex-looking pointer arithmetic.
This line of code, this is pure intimidation. It's designed to make you panic. It's an expression with a 2D array, and it's written in the most confusing way possible on purpose. But here's the thing. Like any scary-looking problem, you beat it by breaking it down into small, manageable pieces. You don't solve it all at once. You chip away at it from the inside out.
Okay, let's tear this thing apart. Order of operations, right? We have to start deep inside with A. Now, for a 2D array, that's just a fancy way of saying A00, the very first element. So let's pretend the value there is 1. We just substitute that in. Now our expression becomes star A plus 1 plus 2 plus 3. That simplifies down to star A plus 3 plus 3. See? Already looking a little less scary.
So now we're left with this. Star times A plus 3 plus 3. What does that mean? Let's work from the inside again. In C, star A plus 3 is the exact same thing as A of 3. It's just a pointer to the 4th row of our array. So we can substitute that in, and the whole thing becomes star A of 3 plus 3. And guess what? That's just the pointer way of writing A of 3 of 3. That whole messy, confusing line of code, it was just a secret identity for a simple array access.
And if we go back and look at the original array from the problem, what's sitting at row 3, column 3? The number 19. Boom. Puzzle solved. Not with crazy math, but just by methodically simplifying the syntax until it made sense.
So, what's the big takeaway from all this? We've looked at 3 different common traps, and each one reveals a key piece of the strategy. So what should you be taking away from this to use on any problem?
Here it is. This is your 3-point strategy to start thinking like an examiner. First, master the details. You saw how one tiny symbol, a bitwise AND versus a logical AND, can change the entire outcome. Second, trace the flow. Don't just read the code, execute it in your head, or better yet, on a piece of paper. Track the variables, track the call stack. And third, visualize memory. Turn that confusing pointer syntax into a simple map of arrays and addresses in your mind. This is the strategy that turns you from just a code writer into a true code analyst. Because when you start thinking this way, these problems stop being tricks and they start being puzzles. You're not just hunting for an answer anymore, you're understanding the very structure of the challenge itself. And that is how you crack the code.